In this video, we're going to learn how to balance an aqueous redox reaction when oxygen or hydrogen are present. And in particular, we're going to learn how to do this in an acidic solution. As a reminder, we can generally classify our aqueous redox reactions into three categories. And in the last video, we worked on how to balance our simple redox reactions. So these are ones that don't have oxygen or hydrogen to balance. And we simply broke those apart into two half reactions, balanced the individual half reactions for mass and then for charge, and added them back together, making sure that the electrons between the two half reactions actually canceled out as we added them back together. We are going to follow a similar process for our redox reactions that contain oxygen and hydrogen, but it turns out that the oxygen and hydrogen, the balancing process for those often involve the water that's the solvent that these reactions are occurring in. And they also involve the charged species that you're going to find in any water solution. So that's the hydrogen ions and hydroxide ions. And it becomes important to know before you get started this balancing process whether you are in an acidic solution, so you have more hydrogen ions for that balancing process, or in a basic solution where you'll have more hydroxide ions available for that balancing process. So you won't be able to tell by looking at an unbalanced redox reaction whether it's occurring in acidic or basic solution. To determine that piece of information, you have to be told that this is actually occurring in acidic solution. So in this particular problem, I am telling you right here, this particular reaction is actually occurring in acid solution, and so we are going to follow a certain series of steps in order to balance our oxygen and hydrogen. If I had told you that it was occurring in basic solution, you would follow that series of steps that we'll cover in the next video. It's going to be the same for your homework. You are going to be told within the problem, the setup of the problem itself, whether or not you're dealing with an acidic or basic solution. So make sure you look for that piece of information in the problem. All right, our first step for balancing these reactions is the same as it is for the simple redox reactions. We're going to separate everything into half reactions. So we're going to take our two reactants here. We've got permanganate ion and we've got oxalate ion. We're going to separate those into two separate half reactions. So my first half reaction is going to be permanganate on the reactant side. And on the product side, I'm going to look over here and find out what permanganate must have become. So the manganese is right here. So that has to be the product for that first half reaction. For the second half reaction, we're going to take my oxalate and we're going to look on the product side for what it becomes. Well, that must be CO2. That has the carbon and the oxygen. Okay, now we've separated into half reactions. We're going to balance those half reactions by mass. So again, we're following that same basic procedure, but it's going to be a little bit different for that mass balancing for the oxygen and the hydrogen. So the first step is just to balance anything that's not oxygen and hydrogen first. So in that first half reaction, I've got manganese. And I've got one atom of manganese on the left and one atom on the right. So that is mass balanced for the manganese. In the second half reaction, I have carbon. So I've got two atoms of carbon on the left-hand formula and only one in the right with carbon dioxide. So I need to raise up the number of carbon on the right-hand side to 2. And we'll just add a coefficient in order to do that. Now remember that that coefficient is actually going to apply to everything in the formula that you placed it in front of. So I now have 2 carbons on each side, but I've also raised the number of oxygens. So that's just a happy accident that we're balancing a little bit of oxygen at the same time, but your focus is really on balancing just that carbon. The reason we added the 2 was to make sure that we had the same number of carbon on each side. Now, we're going to balance that oxygen not by adjusting coefficients, but we're actually going to add water. So the first half reaction is a great example of why we do this. We've got 4 oxygens on the left-hand side, but I don't have any term on the right-hand side that even contains oxygen. So I wouldn't be able to add coefficients anyway. What I need to do is actually add something that contains oxygen. Well, this is occurring in an aqueous solution, so the most likely substance that you have that contains oxygen, the most abundant one, is going to be water. So that's what we're going to add. We're going to add it to the side that needs oxygen, and however many oxygen we need to balance. So I've got 4 on the left. I need to add 4 oxygens to the right. So I'm going to add 4 water molecules, 4 H2O. Now you should be saying, wait a second, now you've added another element that needs to be balanced. Now we've got to worry about that hydrogen as well. You're absolutely right, we do. But we also know that this occurs in acidic solution. It's occurring in water. In any solution of water, you're going to have those charged species of hydrogen ions and hydroxide ions. So what we're going to do for this one, we're going to balance our hydrogen by adding H+ ions. So I just added 8 hydrogens on the right-hand side with that water. I am going to add 8 hydrogens on the left-hand side. Now, this first half reaction is balanced in terms of everything. We've got 1 manganese and 1 manganese. We've got 4 oxygens and 4 oxygens in the water. We've got 8 hydrogens on the left and 8 hydrogens on the right. Let's look at that second half reaction. We know our carbon is balanced. It turns out that adding that 2 coefficient did balance our oxygen for us. We've got 4 on the left, and now we have 2 times the 2 subscript, so that means 4 oxygens on the right. So that's actually already mass balanced for our oxygen, and we don't need to add any additional water to take care of anything. So we can move on to the next step. We are going to balance both of these half reactions by charge. And we're going to do this the same way that we did it for the simple half reactions. We're going to add electrons to the more positive side and the number of electrons that we need to bring both sides of the half reactions to the same charge. What I have to do, these are going to be a little bit more complicated because I'm going to have water and hydrogen usually. I'm going to have to figure out the total charge on each side to figure out which one is more positive. So on the left-hand side for that first half reaction, I have 8 hydrogen ions, each with a +1 charge. So I've got 8 times +1, plus I've got 1 permanganate. For the charge on this, I'm just going to look at that simple charge symbol in the upper right-hand corner. I know this is a polyatomic. We're not going to worry about it as a polyatomic. We're just going to say this entire ion has a charge of -1. So I am combining +8 and -1. That means that my total charge on this side is +7. On the right-hand side, I've got the 1 manganese ion. That's a +2 charge. And then I've got 4 waters. Well, the water is neutral, right? There's no charge up here. So that's 4 times 0, which just gives us 0. So when I add these 2 charges together, I end up with a total charge of +2. Right, now it makes it easier to see where to add the electrons and how many to add. This is my more positive side, the one that has +7. So this is the side that we're going to add our electrons to. And we are going to add 5 electrons, bring that total charge down to +2. Okay, we're going to do the same process for the second half reaction. So here, we've only got 1 ion with a -2 charge. And on the right-hand side, we've got CO2, which is neutral. There's no charge in that upper right-hand corner. So it's 2 times 0, which is still just 0. All right, 0 is more positive than -2. So that means we're going to add our electrons to this side, to the carbon dioxide side. I need to bring it down to -2, so I am going to add 2 electrons here. And now my reactions are charge balanced as well as mass balanced. Okay, so let me erase these individual charges, and then we'll move to the next step. All right, in our next step, we're going to balance the electrons between our half reactions. So we want to make sure we've got 5 electrons in the first reaction and 2 electrons in the second, that when we add these together, they're going to cancel each other out. So they have to be the same number. Now, it's not quite as easy to raise 2 up to 5, since 5 is an odd number. So we're going to go for the least common multiple of those. We're going to raise them up to 10 electrons total between the 2 reactions. So that means I am actually going to multiply this entire first reaction by 2. That will give me 10 electrons. But to maintain that mass and charge balance that I just worked so hard to get, I need to make sure that I multiply everything in that equation by 2. For the second half reaction, I'm going to multiply everything by 5 in order to get that 10 electrons. Okay, so I'm going to rewrite these equations down below with those coefficients multiplied through. So 2 times 8 becomes 16 H plus 2 permanganate plus 10 electrons. And on the right-hand side, I've got 2 manganeses plus 8 waters. For the second half reaction, I've got 5 oxalate ions and 10 CO2 plus 10 electrons. Okay, so now I have the same number of electrons. When I add these 2 equations back together, they're going to cancel each other out. I want to point out something before we go forward, though. I want to remind you that if you get to this stage and you realize that you have both of your electrons, for both of your half reactions, they're on the same side. So they're both on the reactant side or they're both on the product side. There's something that's gone wrong in your balancing process, and you need to go back and figure out what it was. If you're balancing correctly, your half reactions should always end up, one of them should have your electrons on the reactant side and one should have them on the product side. I also want to point out that we can now label these half reactions as either oxidation or reduction based upon where we place those electrons. So on the first one, the electrons are a reactant. That means we've gained electrons, and you know that gain electrons equals reduction. So this is my reduction half reaction, the first one. Loss of electrons equals oxidation. So electrons on the product side means that they're being lost, they're being pulled away from our original reactant. So this second reaction, where we've got the electrons on the product side, is my oxidation half reaction. For my net balanced redox reaction, we just add those 2 half reactions, the reduction and the oxidation, together. So again, you should always have one half reaction that's reduction, one half reaction that's oxidation. You cannot have half reactions that are both reduction or both oxidation. Okay, so let's add these together. We're going to cancel out our common species. So here I can see 10 electrons and 10 electrons. That's going to cancel. And this is a little bit more complicated for my half reactions. I've got a lot more terms. So we're just going to make sure that we don't have anything else that's going to cancel that's in common. Because you might have water, you might have hydrogen ions on opposite sides of the arrow for these half reactions. But in this particular example, we don't. We just have the one water and one set of hydrogen. So nothing that's going to cancel out there. So now we can just bring everything else down to get our final balanced redox equation. So we have 16 hydrogens plus 2 permanganates plus 5 oxalates. And on the product side, we've got 2 manganese plus 8 waters plus 10 carbon dioxides. Okay, we are going to just double check. Let's see, we've done our 5th step here. We've added our half reactions, canceling the electrons in common species. So it's always good to just double check that you really have maintained your mass balance and your charge balance. So for our mass balance, I've got 16 hydrogens on the left-hand side. I have 8 times 2, or 16 on the right-hand side. I have 2 manganese ions on the left-hand side. I've got 2 manganese on the right-hand side. I'm going to skip oxygen for a second. I'll come back to that. I've got 10 total carbons on the left-hand side, and I've got 10 on the right-hand side. For my oxygen, I have to combine 2 different terms here. I've got 2 times 4, that's 8 oxygens here, plus 5 times 4, that's 20 oxygens. So that's 28 total oxygens on the left-hand side. On the right-hand side, I've got 8 times 1 in that water molecule, and I've also got 10 times 2, which is 20 in the carbon dioxide. So that is actually 28 oxygens as well. So let me just write that underneath so that you can see that, where those came from. So that's 2 times 4 for my oxygens, plus 5 times 4 for my oxygens in the second term. That gives me 28 total oxygens. In this term, I've got 8 times 1 for my water, plus 10 times 2 for my carbon dioxide. That also gives me 28 oxygens total on the right-hand side. All right, this is mass balanced. Now we're going to deal with that charge balance. So for the charge balance, we're going to add up all the charges on the left-hand side and compare it to all the charges on the right-hand side. So for that first term, I have 16 hydrogen ions, each with a +1 charge. So that's 16 times +1, my charge, plus 2 times that -1 charge, so 2 times -1, plus 5 times that -2 charge. Okay, positive 16 plus -2 plus -10 gives me a total charge on this side of +4. Okay, let's check it over here. Well, this one's a little bit simpler because I've got a lot of neutral species. So I have 2 times the +2 for manganese, plus 8 times 0, since water is neutral, plus 10 times 0, since carbon dioxide is neutral. Well, that just all adds up together to give me +4. So this is charge balanced as well. Okay, now I know that this final equation that I wrote is both mass balanced and charge balanced, and I am done. This is my correctly balanced redox equation. We had to pull in the water and the hydrogen ions that are present in that acidic solution, but we got it balanced. Let's look at another example. So again, we're being told that this is occurring in acidic solution. Look for that piece of information in the problems that you're given. And our first step for balancing this particular equation is going to be to separate it into half reactions. So I am going to take each of these reactants. I have bromine and iodide, and they'll become the reactants in my separated half reactions. So I'll take bromine first, And what it becomes on the product side, I find it again in the bromide ion. So that'll be my product in that first half reaction. The iodide will be my reactant in the second half reaction. And on the product side, I find the iodine now in the iodate ion. So that'll be my product for that one. Okay, next, we're going to balance these half reactions by mass. And we'll start with anything that is not oxygen or hydrogen. So in the first half reaction, I have bromine. I've got 2 on the left-hand side. I need to raise the right-hand side up to 2. So I'm going to add a coefficient of 2 right in front of that bromide ion. In the second half reaction, I have iodine and oxygen. So for the iodine, I've got 1 on the left and 1 on the right. So that is already mass balanced. Now we've done everything except that oxygen, so we can move on to the next step. We're going to balance the oxygen by adding water to the side that lacks oxygen. So I've got 3 oxygens on the right in that second half reaction. I need to add oxygen to the left-hand side. So I'm going to add 3 water molecules. And of course, I have just added hydrogen, so I'll have to add something to account for that as well. Since this is an acidic solution, we can add hydrogen ions, and I can add it to the side that needs hydrogen. So I've added 6 hydrogens to the left. I'm going to add 6 hydrogen ions to the right. And now both of my half reactions are mass balanced. So we can move to the next step and balance those half reactions for charge by adjusting the number of electrons. Okay, so I need to figure out the total charge on each side of these half reactions first. And for the first half reaction, I just have bromine. There's no charge on this bromine. You don't see any charge number written here in the upper right-hand corner. So that means this is neutral, so I have a 0 charge. On the other side, I've got 2 of those negatively charged bromide ions. So it's 2 times -1. That gives me a total charge of -2. Well, 0 is definitely more positive than -2. So the 0 side is the one that I'm going to add my electrons to. And I'm going to add 2 electrons total to bring that charge on the left down to -2. Okay, we're going to do the same thing for the second half reaction. We've got to add all of these terms, their charges together, to figure out my total charge. So I've got a -1 for the iodide. My water is neutral. Again, there's no charge there, so that's 3 times 0, which is just 0. So this gives me a total charge on the left of -1. On the right-hand side, I have -1 for my iodate, that charge right there. Plus, I've got 6 hydrogen ions now, so each of those has a +1 charge. So that is going to give me -1 plus +6, a total charge of +5. Okay, +5 is definitely more positive than -1, so this is the side we're going to add my electrons to, and I have to add 6 electrons to actually bring that +5 value down to -1, the same charge on the other side. Now, my half reactions are balanced in terms of both mass and charge. And I can do as a quick double check, I can make sure that my electrons are on opposite sides in these half reactions. So here in the first one, my electrons are on the reactant side. That means that this is the reduction half reaction. We're gaining electrons. And in the second half reaction, the electrons are on the other side, they're a product, which means this is oxidation for that half reaction, and the electrons are on the product side. And just remember, at this stage, you should always have one of your half reactions that is reduction, the other one is oxidation. If you ever find that your electrons are on the same side of the arrow in both of your half reactions, so you've got 2 reduction half reactions, for example, or 2 oxidation half reactions, something got messed up in that mass and charge balance, and you need to go back and figure out what it was. Okay, so let me erase these individual charges. And we're going to move to our next step, which is to balance the electrons between the half reactions so that we can actually add them together and have our electrons cancel out. Okay. So I have, in the first half reaction, I've got 2 electrons. Second one is 6. I can easily raise 2 up to 6 by multiplying this first half reaction and everything in it by 3. So that's what I'll do. And I'm going to rewrite that particular half reaction down below, factoring in that 3. So I've got 3 Br2 plus 6 electrons becomes 6 bromide ions. All right. Now we should be able to add these 2 half reactions together and cancel out the electrons and anything else that might be in common. And it does turn out that in this particular process, that it's just the electrons that are in common. When I look through the rest of my reactants and products, I don't see anything that's the same. So I can actually just follow through and add everything down. So here we've got iodide plus 3 waters plus 3 bromine. And on the product side, we have iodate plus my 6 hydrogen ions plus 6 bromide. Now we're just going to do a quick double check to make sure everything is balanced in terms of both mass and charge. So for mass, I've got 1 iodide and 1 iodide. I have 6 total hydrogens here and 6 total hydrogens there. I have 3 oxygens in that water molecule, and I have 3 oxygens on the right-hand side in the iodate. I forgot my charge on that iodate. Let me just add in that negative charge. Okay, and then for my bromine, I have 3 times 2 or 6 bromine, and I've got 6 bromine on the right-hand side. So it is mass balanced. We'll just do a quick double check of the charge balance as well. So for the charge, my iodide is a -1. I've got 3 pulling down my coefficient times the 0 charge for the water because it's neutral. There's no charge written in that upper right-hand corner. And I've also got 3 times the 0 charge for the bromine. So this all adds together to give me a -1 charge total on the left-hand side. On the right-hand side, I have a -1 for that iodate, just pulling down the charge. Plus, I've got 6 of those +1 hydrogen ions and 6 of the -1 charge on that bromide ion. Well, if we add all of those terms together, it also ends up giving us -1. So we're charge balanced as well. We've got the same charge on each side of that arrow. Okay, so now we know that this particular chemical equation, it is mass balanced, it is charge balanced, and this is our final answer. All right, now we have covered how to balance simple redox reactions. We have covered how to balance redox reactions that have oxygen and hydrogen in acidic solution. In the next video, we'll look at how we do this when the reaction occurs in basic solution.